Thank you everyone for coming and welcome to the Tacklebox presentation. My name is Juan. I'm here with Kyle, Kevin, and Armando, and we're a fully remote team spread across the US. As you already know, we're here to talk about Tacklebox. So what is Tacklebox? Tacklebox is an open source serverless framework that offers webhooks as a service. Now, don't worry if that seems like a mouthful, because it is. So we'll try to unpack the meaning behind that phrase throughout the presentation. Tacklebox as a project includes a CLI tool, a management UI, 4 client libraries, which are written in JavaScript, Ruby, Python, and Go, and a webhook service, which comprises a RESTful API and AWS infrastructure. Now, an overview of the whole presentation is as follows. First, we'll give you some context around the world of webhooks. Then we'll explain why building webhooks well is hard. Next, we'll explore some of the already implemented solutions in the real world. After that, we'll talk about what Tacklebox is all about. Then we'll get into the nitty-gritty stuff of how we actually got to the final implementation of Tacklebox. And last but not least, we'll talk about some future ideas. So without further ado, let's jump right in. In this first section, to give you context around webhooks, we're going to talk about a couple of things. First, we'll define what the word webhook means. Next, we'll talk about current users of this tool. And lastly, we'll talk about things to consider when building webhooks. To understand what webhooks are, let's begin with an example using a tool that we all know, GitHub. Imagine you're a part of a team. You have one repo for the project the team will work on, and you want to do something programmatically when a branch is created by a teammate, like for example, post a message on Slack or something like that. The flow would look something like this. First, one of your teammates creates a new branch locally. Then the change is pushed to the repo. Next, the branch is actually created on the repo. And finally, you want to do something programmatically as a result of this branch creation. So the question then becomes, how can you automate what you want to do once the event happens, which in this case is a branch being created? Well, you basically have 2 options, polling and webhooks. In the context of web APIs, the party interested in data, which in this case it's you, is called the consumer. And the party that provides the data of interest, which in this case it's GitHub, is called the provider. With polling, you basically send an HTTP request to GitHub every so often to see if there's any updates. In this case, you happen to send a couple requests first with no updates from GitHub, and then a third one where there is an update. With webhooks, however, instead of having GitHub wait for incoming requests in order to handle them, now GitHub proactively sends an HTTP request to you every time an event you care about occurs. To be more specific, GitHub sends an HTTP request every time something of interest happens to a URL that you register with them. In this particular case, a branch was created, so GitHub sends an HTTP request to your endpoint, and you then acknowledge the request. In other words, a webhook is nothing more than an HTTP request sent when an event happens. Now, up to this point, we have only talked about webhooks from the perspective of the consumer. Let's switch gears a bit to talk about webhooks from the perspective of the provider, which in the example was GitHub. In other words, let's put ourselves in GitHub's shoes. Following the same example, if we are GitHub and a consumer is interested in receiving a webhook every time a branch is created, the workflow would look something like this. First, you receive a subscription request with a URL to send webhooks to, which will be the URL on the right of the slide, which reads sendrequestshere.io. This subscription request also specifies the event type that the consumer cares about, which in this case is a branch creation. Then you'll persist the subscription. After that, a branch is created at some point in time. Then you check to see who is subscribed to what event type, since there may be more interested parties. And lastly, you send a webhook to the URL of each consumer subscribed to that particular event type, which in this case, for simplicity's sake, is just the consumer from step 1. To show you how webhooks look like in real applications, here's a screenshot of the UI GitHub offers for webhooks. Up to the right, you can see an add button, which will be used to request a subscription. After clicking that button, you get to the page where you specify the URL where you want to receive webhooks, the event type you're interested in, among other things. And once you register a URL to receive webhooks, you can see all the webhooks that GitHub has sent, their headers, their payload, etc. So far, when talking about webhooks, we've only talked about GitHub. However, it turns out that GitHub is not the only company that offers webhooks. Some examples of companies that also offer webhooks are Stripe, which can send you a webhook when, for example, a payment is processed. Twitter, which can send you a webhook when, for example, you receive a direct message. Intuit, the company that owns products like TurboTax and QuickBooks, can send you a webhook when, for example, a budget is created. And I mean, I can keep going. The point is, webhooks are everywhere. Now that we have some context around webhooks, we can start talking about things to consider when building them. As a provider, webhooks offer a few benefits. For example, you can provide a better experience to your users that want or need webhooks. And also, you can lower the amount of requests your infrastructure needs to handle over time. However, webhooks are not perfect. If you want a very simple webhooks implementation, it may not take you too long to implement. However, if you want a robust implementation, you have to spend a lot of time and effort building it. Now, the reason you have to spend a lot of time and effort building webhooks well is because building webhooks well is not easy. We're going to talk about why building webhooks well is not easy in the next section. In this section, we're going to explain why a robust webhooks implementation can get really complicated really fast. First, we'll talk about the first challenges that may come to mind. Next, we'll show you what it looks like to implement webhooks well in one app. Then, we'll show you what it looks like to implement webhooks well in multiple apps. And lastly, we'll talk about abstracting away this implementation. Now you, the provider, want to build webhooks in your app. However, implementing webhooks well is not as trivial as it may seem at first glance. Since we can go down a rabbit hole here, we decided to talk about 4 different areas or categories that may present a significant amount of challenges. The first area that comes to mind when thinking about building webhooks is failed messages or endpoint failure. For example, what happens if a consumer URL fails or is unreachable? Do you try to send the message again? And if you do, how often and how many times do you retry before you stop? The second area that comes to mind is security and authentication. For instance, do you want to make sure the appropriate consumer controls an endpoint before you send messages to it? How do you allow consumers to verify the integrity of messages? And how about allowing them to verify the origin of messages? The third area revolves around monitoring. For example, how do you identify frequently failing endpoints? And how do you monitor historical usage patterns? And last but not least, we have the area of consumer experience. For instance, do you want to allow your consumers to manually trigger events for testing or other purposes? Like, for example, aside from testing, do you want to allow them to resend a message manually? And if you do, how would you implement that? In the simplest scenario, building webhooks in one app would look something like this. Now, for simplicity, we have 2 consumers only, but there could be more. And all these concerns we have would fall into this new webhook implementation in this single app. But what if you need webhooks in more than one app? Well, if you implement webhooks in more than one app, it would look something like this. Now, you have all the concerns from before times the number of apps that you have. And on top of that, more questions come up in this scenario. For example, how do you avoid redundant work while implementing and maintaining webhooks across all your apps? How do you make sure that webhooks are consistent across all your apps? And lastly, is governance or compliance critical to your apps? And if so, how do you enforce control over your data? At this point, the need for building a robust webhooks implementation as its own service becomes clear. Now, all these concerns are abstracted away by this service, and this would give you many benefits. For example, first, you would have a single place to maintain code and add features. Also, you would have a single place to monitor the service performance and other metrics. Aside from that, you would have one place to manage related infrastructure. Also, you could have consistency across all the apps. Aside from that, now the apps don't have to be aware of who is consuming their webhooks, allowing more focus on business logic. And last but not least, now you would have centralized control over data in order to enforce governance or compliance if those are important for your apps. Now I'm going to pass it over to Kyle to tell you a bit about current webhook implementations.
Thanks, Juan. So for this section, I'm going to give a high-level overview of how a couple of companies implemented their webhook solution. I'll walk through a couple of options to go with if you decide that you don't want to implement webhooks yourself. I'll then dive a bit deeper into the pros and cons of the commercial versus DIY options. And finally, I'll talk about some specific use cases that our framework is geared toward. So if you're thinking about implementing a webhook solution yourself, the question that naturally arises is, how do I do that? Thankfully, as we saw earlier, many companies have already implemented their own in-house solution and posted their learnings online. So there are quite a few blueprints out there. We took particular inspiration from how Square went about implementing this feature themselves. Some key features that we liked were how they used a queue for messages waiting to be sent to subscribers, how they used Lambdas to dequeue messages and send them to subscribers, and how they went about storing successful or failed messages in a separate queue or database. We also liked Wise Engineering's webhook service implementation. They utilized Amazon's simple notification service to handle consumer subscriptions. This meant that in regards to figuring out which subscriptions needed to be notified when an event happens, sending messages to subscribing endpoints when the event is actually triggered, and handling the retry logic for failed messages, all of these operations were extracted from the main app logic and were handled by a single service, SNS. As we mentioned earlier, trying to build webhooks and integrate them, even in just one app, can be a very complex thing to do. So as you think about trying to expand that out to multiple different apps in your ecosystem, that can be very difficult and time-consuming. Let's say, for instance, that you decide that you don't want to do that because of complexity, and you'd rather offload that to a third-party provider. Generally, you would have 2 options, either a commercial solution or an open source solution. Unfortunately, there currently isn't an open source solution that provides webhooks as a service, so that really only leaves us with the commercial solutions or building it ourselves. If you decide to go the commercial route, there are a couple of companies that offer webhooks as a service. The general workflow when using the commercial solutions would be as follows. You, the provider, communicate with their service via API calls to set up subscriptions, create event types, send messages when an event is triggered, and access message history. The commercial solutions handle the data storage, message sending processes, and general infrastructure management. The trade-offs that arise when using commercial solutions would be the fact that you'd be sharing data with a third-party vendor, and there would be a lack of software customization because it isn't open source. As we saw earlier, there are a number of large existing companies that offer webhooks to their customers, like GitHub, Stripe, Twitter, and Square. They had to build their own solutions in-house and manage their own infrastructure, but by accepting those trade-offs, they were able to have control over their data and customize their solution to better suit their business needs as they changed. By examining the pros and cons of each approach, we set out to create an open source framework that's easy to deploy and manage, and that's where Tacklebox comes into play. So who is Tacklebox geared toward? A good way to find out is to ask yourself these 4 questions. Do you want to be able to easily integrate this feature across multiple applications? Do you want to have control over your data? Is your app small to medium sized? And is your application's core competency anything but webhooks? If you answered yes to all of the above questions, then Tacklebox would likely be a good fit for you. In this section, I'm going to talk about the goals of our project and how to deploy each piece. I'll highlight how each feature accomplishes the aforementioned goals. I'll walk through a brief demo to give you some ideas of how to use Tacklebox. And finally, we'll look at how to tear down Tacklebox if you no longer need it. So we had 3 goals in mind when creating Tacklebox. We wanted to make it easy to provide webhooks across multiple applications. We wanted to make it easy to deploy and manage its infrastructure. And we wanted to make it easy to integrate with an application. So to realize the goal of easy deployment, we created our framework in such a way that deployment is abstracted to one simple command, Tacklebox deploy. This process usually takes upwards of 20 minutes, but is sped up for demo purposes. As you can see here, the output of the deployment has 2 parts. First, the API host, which is the base URL you'll use to communicate with the Tacklebox API. And second, the API key, which is the key the Tacklebox API uses to authenticate you. These 2 pieces of information are all you need to communicate with our API, and you don't have to leave your CLI to retrieve them. After running Tacklebox deploy, you can run the management UI on your local server with one command, Tacklebox UI. This management UI ties back to making it easy to provide webhooks across multiple applications. Instead of having to make API calls to figure out the KPIs of your webhooks feature for one of your apps, you can just view it all in a convenient dashboard, which looks like this. To make our framework even easier to manage across your apps, we provided client libraries in 4 languages to make using the Tacklebox framework standard and dry. Now we're going to show a brief demo of Tacklebox in action. So imagine that you're a software engineer at a consumer electronics company, and you're tasked with enabling automatic notifications from the purchase order app to several other supply chain apps. The initial workflow when using Tacklebox is to register a service by providing the name of it in a JSON body. This service, in this case, is going to be our order app. This is the app that's going to be providing webhooks. Now that we've created a service, we can use its ID and the path parameters to register an event type that users can subscribe to. In this case, we want notifications to be sent whenever a purchase order is created, So we'll call the event type order created. Next, you can create users in order to group their endpoints in one place and ensure that they only receive messages intended for them. Something to note here as well is that users, aka entities that are interested in being notified of an event occurrence, can be thought of in a few different ways depending on the use case. In our example, the users are other supply chain apps, like our invoice app here. That the invoice app wants to be notified whenever a purchase order is created. For GitHub, their users are repositories. For a to-do app, the user could be the actual user who signed up. Just something to keep in mind here. So in the same way that we use the service ID to create event types, we can use the user ID to register endpoints. After providing the user ID and the path parameters, we also include the URL and event types that this endpoint will be subscribed to. In this case, the invoice app only cares about being notified when a purchase order is generated. So that is the only event type that we list here. So after the initial setup, we can view our management dashboard for the service we just registered. Currently, we are viewing the dashboard for the order app, and there's only one user and one endpoint. From here, we are able to view more granular details about the user, event type, and endpoint that was just created. So here on the left, we have our purchase order app. And on the right, we have an endpoint that our user registered for notifications. So let's say a purchase order for 5 computers is created. This triggers a message to be sent to the subscribing endpoints, which can then view the webhook content and take action accordingly. So going back to our management dashboard after the triggered event, we see the corresponding data has updated accordingly, with one event being triggered and one message being sent. From here, we are also able to view more granular details about the recently triggered event, as well as the corresponding message that was sent. If you decide that you no longer need the webhooks feature, then you can simply remove the infrastructure with one simple command: Tacklebox destroy. This pulls down the entire infrastructure of the entire Tacklebox framework. Now I'm going to pass it over to Kevin to talk about how we went about building Tacklebox.
Thanks, Kyle. Okay, so in this section, I'm going to go over how we built Tacklebox, and I hope that this will make a little more sense now that we've shown how it actually works. And we're also going to go into some of the implementation decisions that we made along the way while we were building this. So it'd be difficult to discuss our architecture without first laying out what we believe to be required features in a webhook service. So we'll spend a bit of time reviewing those. After discussing required features, we thought it would be helpful to spend some additional time talking about the event message lifecycle, which we consider to be the core of our service. Next, we'll give a brief overview of Tacklebox's architecture and how it relates to the event message lifecycle. And finally, we're going to discuss a few of the challenges that we faced along the way and how they influenced our implementation. So first, feature requirements. Since consolidation is a key part of our use case, allowing multiple applications to use Tacklebox simultaneously was important to us. We wanted to allow providers to specify event types when setting up their webhook service. So recalling that GitHub example, their webhooks feature would be less useful if it was an all or nothing approach. Allowing granular control over these event types is important. Next, we wanted to provide easy access to message history. So this includes two distinct parts, persisting every message sent by Tacklebox, along with delivery statuses, and providing an interface to view that message history. Finally, we wanted to send messages to consumers when events occur. Again, this is the central piece of Tacklebox. Without this, it's not a webhook service. And as a side note here, I want to mention that while this message delivery often occurs shortly after an event notification is sent to Tacklebox, delivery speed was not a primary goal for us. The core functionality of a webhook service is sending messages to endpoints when events occur. That process might include the following steps. An event occurs in an application, and that application notifies the webhook service. The webhook service looks at the event type and gathers a list of subscribers that need to be notified. The webhook service sends a message to every valid subscriber, letting them know that an event has occurred. If any message delivery fails, the webhook service attempts to resend the message either until it succeeds or until it reaches a set number of attempts. Each message and its result gets saved to the database, regardless of whether or not it was successful. So with this lifecycle in mind, we're going to map it onto our final Tacklebox architecture. So again, I said final Tacklebox architecture. On this slide, we're going to talk about what our final implementation looked like. And a lot of this may not make sense without context, but we'll get into the context afterwards when we discuss challenges. So in our architecture, notification intake is handled by a pair of services, API Gateway and Lambda functions. API Gateway serves as the entry point into Tacklebox and passes incoming notifications to an intake Lambda. The next two steps in the lifecycle, gathering consumers and sending messages, are handled by the simple notification service. The last step, saving messages to the database, is taken care of by a combination of a log service, CloudWatch logs, and a Lambda that transfers message information from those logs to our database. So now, even though we're going to be focusing almost exclusively on the event message lifecycle as we discuss our architecture moving forward, I did want to add a quick comment about how our architecture handles basic processes like adding, updating, and deleting entities. Generally speaking, almost all of our CRUD operations are handled by our intake Lambda, which communicates directly with the database as needed. Because of our focus on the event message lifecycle, we're going to call our database the message history moving forward, but this is really a store for all of our persistent data, including applications, users, event types, etc. Also, there are a few processes that require touching both the database and SNS, like creating or updating a subscription, and in those cases, the Lambda again orchestrates the process. Okay, so now that we've shown the end result for our architecture, we're going to talk about some of the challenges we faced along the way. Again, these challenges influenced our implementation and are how we went from our initial approach to that final architecture. These challenges are how we dealt with wasted uptime, how we handled the message fan-out process, and how we persisted message history. Our initial implementation of Tacklebox used a single application server. It could have worked for our use case, but we saw an opportunity to optimize our infrastructure. Webhook usage patterns are often unpredictable, can have moments of high use as well as periods of minimal usage. As a result, with this single app server architecture, we may have had a lot of unused compute resources. To address this, we decided to use AWS Lambda functions. Lambda functions, which are AWS's function as a service offering, allow us to only run code when needed. Lambdas, of course, come with trade-offs. So first of all, cold start times can increase latency. And cold start time refers to the time that it takes to load the function into memory before it can be invoked. Lambdas are stateless, so accessing persistent data requires a call to another service. And finally, each Lambda has an execution time limit. Currently, this is set to 15 minutes. We were okay with these trade-offs, so we decided to use Lambdas. Going with Lambdas, though, meant that each Lambda would have to do all of the following tasks every time it runs. They would need to intake a new event and persist it to the database, gather subscriptions and create messages for each consumer, send messages to all consumers and wait for their responses, and write responses to the database. Finally, they respond back to the event producer after all of these tasks are done. So this is a lot of responsibility and potentially a lot of execution time for a single function. So while we believed Lambdas improved our architecture, they also added some additional challenges that we wanted to address. To explain these remaining challenges and how they influenced our architecture, I'm going to go ahead and pass it off to Armondo.
Awesome. Thanks, Kevin. So as Kevin just mentioned, our Lambdas are currently doing a lot of jobs. And the message fan-out process in particular is expensive. So in our current design, when an event comes in, a Lambda function gets fired up and creates a list of messages that need to be sent to each consumer listening for that event type. Now the Lambda not only has to send the messages, but also has to wait for a response from everyone before it can finish its work by writing the results to the message history. And because webhooks are typically application or user specific, the number of consumers needing to be notified is typically pretty low. However, there are use cases where the number of consumers is high. As the number of consumers increases, so do the number of HTTP requests and the probability that one of the consumer's endpoints is going to fail. And when we think about consumer endpoints that fail, as in they time out or are unreachable, the burden still lies with the same Lambda. Retrying failed messages is a key part of a webhook service. So in addition to sending its original set of messages, the Lambda would also need to repeatedly try to resend failed messages before it can write to the database and finish its execution. And using exponential backoff, which is a common algorithm used in retry logic that increases the amount of time between successive retries, means that with every failed attempt, the Lambda is going to have to run even longer until it reaches the maximum number of retries or Lambda's 15-minute execution time cap. So in order to reduce the strain on our Lambdas, we could have done a couple things. So we could have added a second type of Lambda, which we'll call a messenger Lambda, which would allow us to separate the message creating, which is what the intake Lambda does, and message sending, which is what this new Lambda would do. With this approach, when an event comes in, our intake Lambda gathers the list of consumers that need messages and calls a separate messenger Lambda to actually send each message. This way, our messenger Lambdas can all run at the same time and don't have to wait for each other to finish. So retries would be difficult to implement though, because where do you put messages that need to be retried? We could have the intake Lambda spin up a new messenger Lambda for each retry, but then the intake Lambda would be again waiting for all retries to finish. We could potentially put them all in the database also, but that's a lot of writing, reading, and deleting for data that's only meant to be temporary. Ideally, we'd have something that can buffer our outgoing messages and have a mechanism to quickly pull them off in order. And that's exactly what a queue would give us. And a queue would also have the added benefit of centralizing our entire outgoing message list in one place, which simplifies debugging. So Amazon's Simple Queue service, or SQS for short, does exactly this. SQS gives us a reliable place to put both our original and retried messages into, which is great because our intake Lambdas can now just focus on creating messages for an event. SQS doesn't send messages to consumers itself, so we keep our messenger Lambdas in place where they are and continue to use them to send messages. The messenger Lambdas check SQS for new messages and pull them off as soon as they appear. So our messenger Lambdas don't have to wait for retries. We have them immediately put failed messages back into the queue so that they can be pulled out at a later time by an entirely different Lambda invocation. So by adding SQS, we've increased the complexity of our implementation a bit, but each piece does fewer things, and we've sufficiently separated our concerns across services suited for their jobs. And this is a perfectly reasonable implementation. However, we wondered if we could eliminate, ironically enough for a webhook service, the polling in our architecture. So our messenger Lambdas use polling to constantly check SQS to see if new messages have been added. And as we mentioned, webhook events can be intermittent, and all of those polling requests in between events can add up. Under the hood, it gets even more interesting because when using Lambdas with SQS, Amazon requires that a minimum of 5 parallel Lambdas poll SQS. So the number of requests is higher still. And when your queue is constantly full, all of this polling is a real benefit because it allows you to dequeue more quickly. But with our use case, there will likely be periods where this is wasteful. If we could eliminate that polling entirely, we could potentially make our implementation even more efficient and reduce latency in the message sending process. So we were able to remove polling from the message sending process by using Amazon's Simple Notification Service, or SNS. SNS is a messaging service that, when given an event, sends a message to every subscriber to that event. It also automatically handles retries. So in other words, it does the same job that the combination of SQS and Messenger Lambda previously did for us. Rather than use polling, SNS uses a pub/sub model where new messages are published to topics, and anyone who subscribed to that topic automatically receives a message. In webhook parlance, every consumer that's listening for that event type receives a message. It's important to note that SNS itself stores subscription data, so that's one more job SNS also handles for us that our Lambdas were previously handling. With SNS, there's no longer a need to pull consumer subscriptions when an event comes in. SNS already knows who needs to be notified. Switching from SQS to SNS simplifies our architecture and removes polling at a key step. However, there are some trade-offs with this approach. SNS has a max retry delay of 1 hour compared to SQS's 12 hours, so it's got less flexibility to implement large retry windows. And because SNS itself keeps track of subscriptions, we now have to ensure that the subscription data in our main database matches what's in SNS. And when changes to subscriptions are made, we have to make the change in 2 places. Other operations like adding new event types also require double maintenance. So both SQS and SNS approaches meet our project goals, and both definitely have their benefits. In the end, we chose SNS because it better fits our use case, and it includes features like rate limiting and customizable retry logic out of the box. Which leads us to our third challenge, persisting messages to our message history. Now, you may have noticed that in the last SNS slide, there wasn't a line between SNS and our database or our message history. That's because SNS doesn't have a built-in way to write message data to our database. And in a way, this kind of makes sense. Its main job is to fan out messages to consumers. And as far as it's concerned, once it delivers a message or makes every effort to with retries, its job is done. So our entire event message lifecycle currently ends the moment SNS sends a message to a consumer and receives a response. The only thing that's actually been saved to our database at that point is the original event itself, which the intake Lambda did, but no message data has been saved. That means no record of who was sent a message and when, what the payload was, what response SNS received back, etc. So we needed to find a way to get message data from SNS into our message history after the message send process completed. So our first thought was to see if we could tack on some post-process to SNS, like a function that executes immediately after it receives a response back from a consumer. SNS doesn't have a built-in way to do that, but it does allow Lambda triggers to be set to run whenever a message is published. Inserting Lambdas here, though, would add more complexity because the Lambda would again be responsible for sending the message to the consumer. And at this point, we're essentially back at our previous SQS implementation. So instead, we found a way to use a service that SNS was already integrated with. SNS stores logging data in Amazon's CloudWatch log service, which is commonly used for things like debugging and a variety of other tasks. SNS can be configured to log specific events, and in this case, we wanted it to log every time it received a response back from a consumer. Using CloudWatch logs, we now had our persistent message store, but it wasn't in the same place as the rest of our data, which is the message history. So we needed to find a way to get it from CloudWatch logs into our message history. Now, CloudWatch logs can be set up to asynchronously invoke a Lambda function. So we set CloudWatch logs to invoke the Lambda when it received a new SNS log. And once invoked, the Lambda transfers the message data in the log to the main message history. Now, in light of these added steps and services, SNS definitely added a bit of complexity to our architecture. However, we still thought that overall its feature set best fit our implementation and provided a few additional nice-to-haves out of the box. And as Kevin showed earlier, this is the implementation we chose in the end, So hopefully you've got a bit more context now as to how and why we ended up with this architecture. And we'd like to finish by just calling out a few features we could potentially add moving forward. So Tacklebox currently does two things by default that, while really useful, are not features all providers might want. The first thing is it requires consumers to confirm their endpoint, meaning they have to verify they're in control of it by taking some action before our service will send any webhook notifications to them. And the second thing is it includes AWS metadata in messages sent to consumers that isn't really relevant to Tacklebox. It's just kind of extra information. So because these are both features of SNS itself, and SNS is the piece of our infrastructure that communicates directly with consumers, we can make both of these optional by putting some logic in between SNS and consumers. So one way we might do that would be to use a proxy server, which would handle the auto confirmations and stripping of metadata. It would allow us to change headers, do a couple of other things. But using a typical server would cause us to lose some of that uptime efficiency we gained by going with Lambdas in the first place. Speaking of which, as you guessed, we could use Lambdas here also to accomplish this. But as we saw in the last section, that extra set of Lambdas again adds complexity to the architecture for a feature that only a small percentage of our users would probably use. Another few things we could add would be the ability to dynamically set and change settings like retry policy and rate limiting on a per consumer basis, a consumer UI that potentially allows them to view their own message history and do things like resend failed messages, a dead letter queue for efficient processing of messages that still, after the max number of retries, failed to be delivered to their consumer endpoint, and a feature that detects when a consumer endpoint has passed some threshold for successive failures and automatically removes that consumer's subscription from our service. And that's Tacklebox. We hope you enjoyed our presentation and know a little more about the simple yet quite complicated world of webhooks, as well as the use case that Tacklebox fills in this space. Thank you.
Okay, awesome. Let's start with questions. So first is actually not a question, but a comment. So one attendee loves your diagrams and animations. It's really helpful to make things clear for us watching your presentation. Nice work. Awesome. And now let's get to questions. So can you talk more about implementing the several client libraries? How difficult was that to implement, and what do you remember about the decision-making process?
I will start that one, and I'm going to let Juan pick that up because the basic flow that we took was I built the initial library in JavaScript, and then Juan was the whiz who translated it into the other three languages. So I'll let him talk about maybe the process of translating it. But as far as building it, it was kind of hard to find some information online about a good way to approach building a client library like this. There was obviously a lot of information about using client libraries. There were some internal Launch School resources that we used to work with APIs in general. But I think at the end of the day, providing a consistent interface for people to use was challenging, but definitely doable within a fairly short amount of time. And I'll let Juan sort of talk about how maybe what the process was like translating it to other languages, because I'm sure that came with its own challenges.
Yeah, definitely. So this was a very good example of, the power of just-in-time learning. Myself, I had never worked with Python before, and writing this library took me one day, at least the Python one. And that's where I realized how important it is to have strong fundamentals, to understand basic programming concepts really well, even if it's in different languages. Because when you try to translate it to another language, it's just a matter of syntax at that point in time. Another part that was really challenging was the publishing part, because each language has its own ecosystem, its own flow, and that part was also really hard to pick up. But in general, it was very gratifying, and it was well worth it.
Okay, awesome. So Rodney says, love the animation. Seems like you had a lot of different data types of data to keep track of. What went into deciding, or how did you decide what kind of database you needed?
That was an interesting question, and definitely one that we spent a fair amount of time discussing. It didn't make it into this presentation, but if you love pain and want to go read our write-up after watching this whole presentation, we are going to put it in there, some notes about that. So I'll just say that obviously the initial question was, do we go with something that's NoSQL, something that's unstructured, or do we use something like Postgres, which is eventually what we ended up with. And our initial thought was, we're providing this service to an unspecified number of people who might use this because it's open source. And with webhooks, each consumer might choose, or each provider might choose to put different types of payloads in there. It could be sort of endless. But at the end of the day, after we sort of dug into it, we realized that of all the data that our service handles, the only thing that's unstructured is the payload. And we can sort of still use a relational database to do that and put the payload into like a JSON-B column and still have it work. And so the benefits that we would have got with going with a NoSQL database, which we definitely could have, we trialed this with DynamoDB, which also worked. There just weren't enough reasons to go to NoSQL, and we felt fine keeping it in the Postgres area. So.
Okay. Did you end up using the AWS CDK to build this out? Seeing the multiple languages, that must have been challenging.
Yes, we did. So the deploy and teardown steps are both done with the CDK. And so our client libraries were actually deployed separately, so we didn't have to worry about packaging those up with our CDK code, but we ran into a lot of other problems by using the CDK. So it was sort of like a double-edged sword there. It made the teardown a lot simpler, and it seemed to make setting it up a lot simpler, but we ran into some strange permissions errors and like race conditions when trying to apply IAM permissions to things that we had just created. So yeah, it added some challenges, but it was not the multi-language challenge.
Okay, Ronnie just said that they also, or his group also had a lot of pain as well, and a lot of discussion with the database choice. And we have a final question, which is, what was experience going from wanting to do something to making it work with AWS?
Ooh, that's a big question. I think in the end, it was really gratifying. I'm going to keep my answer short because I kind of want to hear what some of the other guys have to say about that. But yeah, it's really cool just to finally see something work. That first time you see a message come through, you kind of do a little fist pump in the air. You're like, all right, this is happening. But learning AWS definitely took some time. But as with most of these things, once we learned it, it did not seem as daunting, for sure.
Yeah, I'll just piggyback on that and say that AWS, if you have never worked with it before, it has a very steep learning curve, especially at first. But like Armondo said, once you get the hang of it, it's all, everything falls into place.
Yeah, and just to add a little bit onto that as well, it was definitely a daunting experience, but going from wanting to do it to actually putting into AWS, I think something that really did help us was some initial advice we got was actually implementing it on a smaller scale, like in one of our own local apps, just a simple webhook feature, and just kind of getting an idea of what it looks like on an elementary level, and then just building from there. So that was definitely a very helpful experience doing that.
Okay, actually, we have more questions. So what did you guys use to build the management UI? Was it Tailwind?
Yeah, I can speak to that. Yes, it was Tailwind. It was not, these were not all bespoke components. Tailwind has a library called Tailwind UI that they offer, which offers like React specific components that you can
use as a template, and then sort of build out however you want. So that's saved us a whole lot of time with like the visual layout. And then we were able to make the tweaks and spend more time actually connecting it behind the scenes with Redux to our API.
Okay, so Owen says, love the dashboard. It seems like a really useful feature for a tool like this. How much work was it to create data visualizations in your dashboard? And what tool did you use for rendering them?
So most of the time, creating those visualizations was finding a library to do it. I thought for like maybe an hour that I was going to do it myself, which was really naive. And I mean, I would have liked to see how it turned out because it would have been a disaster. But I went with Chart.js in the end, and there was a React specific library that sort of packaged up this Chart.js library and made it easier to use.
Okay. And the final question, what was your favorite part of working on Tacklebox? Yes, that's question for all.
For me, I really liked working on the CDK to try to get the automatic deployment up and running. I felt like it was really fun to do because I felt like I was able to see from start to finish like the different resources that needed to be provisioned and just kind of the intricacies that were involved in working with each one. And just finally seeing it come together into one simple command to get it all deployed was really fun.
Yeah, I definitely agree with that. I think after having built this, I think it's interesting to note. I thought I feel really proud of what we built, and at the same time, you start to zero in on these like really, really tiny, insignificant things. Like, oh, I got to fix this thing. Like, you know, there's an extra space here. Like, I got to handle that. And so I think, you know, maybe it's like a parent thing or something. But once you release that thing into the world, you're like, you always worry about it, I think. And so it's the same with this. Like, the job's never done. I think we're super proud of what we got here, and it definitely meets all of our goals. But I don't know, you can always do more, you know?
Since no one else has said it, I'll say the relationships I made along the way, which I, you know, it's true. I mean, it ended up good. Learning to work in a group was just this really this piece that I underestimated, and it was challenging in many ways. But I thought it was cool how you know, you learn that everybody wants the same thing, and even if you have different ways to go about it, if you can just be patient and kind with each other, that it's going to turn out better for everybody in the end. And if you try to rush ahead on your own and get to like 10% more finished, but you sacrifice those relationships on the way, it's probably not worth it, and you're not going to look back on it very happily.
And I'll piggyback on what Kevin just said. Coming from core, which can be a very isolating experience, very tough, very full of stress, and just a path that you have to walk on mostly like alone if you don't have the time to meet with others or just be part of the community as much, like it was my case because I had a full-time job and, well, life circumstances. Being part of a team where everyone had strong fundamentals, where you could have discussions about very complex topics, about very clearly, while always being respectful, kind with one another. It's something that I had never experienced before. It was really, really gratifying. And it was also very challenging because, working with people who are, just great at what they do, brilliant, is just, it's a lot, and you basically have a high bar set. But, with the preparation that we get from core, it was definitely doable. And here we are. We did it.
Yeah, awesome work. Any final words?
I just want to say thanks again for everyone who popped in.
Yeah, thank you.
Yeah, thank you guys.
That's about it.
Thank you. Yeah.